Hi, welcome to the series of videos for pupils studying OCR 21st Century Science. This is Unit P5 about electricity, and this is Lesson 7, and we're looking at parallel circuits. We're going to look at how you know a circuit is parallel, what happens to the current in parallel, what happens to potential difference in parallel, and what happens to cells in parallel. Why would we bother putting cells in parallel? A parallel circuit is one where at some point the current splits up. So you can identify a parallel circuit by the fact that you have a place where the circuit splits up, and then you should have a place where the current joins back together again. So this is what happens in a parallel circuit. Current in this one is going to flow towards the plus end of the battery from the negative end, so it flows around here. And when it gets to this point here, some of the current will flow through this branch and some of it will flow through this branch. And then it will join up again and flow back to the battery, or the power supply. So we know we have a parallel circuit when the current splits up. And I'll put in brackets, and it should rejoin at some point as well. So how do you know it's parallel? Because it's not a single loop. It's somewhere where the current splits up. Oftentimes you might find the circuits drawn like this, and maybe it's less obvious that they're splitting up. For example, but you can see the same thing's going to happen here, which is current will flow around here. Some goes that way, some carries on, some carries on, some goes through there. I'm realising that yellow is not the most easy colour to see. And then it joins up again. So current splits at this point. Some goes up there, the rest goes this way. Some goes up there, the rest goes this way. Around, and we get the same thing joining up again at the other end. So that's how you know you've got a parallel circuit, if the current splits up. Now, because the current splits up, then the current will change its size. Now, I'm going to add a cheeky ammeter in here, and if this ammeter reads 5 amps, for example, then the current will split up between these two branches. Now, if these bulbs are identical, then the current will split perfectly in half. So I'd get 2.5 amps and 2.5 amps in each branch before it goes back together again and becomes 5 amps again. So you can think of this idea of having the main circuit current. So this is the main circuit, which is bigger, and then when it gets to here, it splits up into two smaller parts, and when it comes back together again, it's a bigger current. So in parallel circuit, the current splits up and rejoins, and the amount of current flowing down each branch depends on the components. If the components are identical, then you'd have the same current flowing in both. But if one bulb had twice the resistance of the other, twice the resistance would mean half the current through that one and twice as much through the other one. So it's split in a ratio. Right, let's look at potential differences in parallel. Current splits up, but the potential difference doesn't split up. Now, one way to think about a parallel circuit when you're doing problems is to consider every component in a parallel circuit acts as if it was the only thing that was connected to the power supply. And this will really help your thinking when solving these puzzles. So here is a parallel circuit. Let's say we've got a resistor here and a different resistor here. Let's call those R2 and R1. So the current comes along here, down to here, splits up, some goes this way, some goes this way, joins back together, back to the cell. But if you think of parallel circuits in the following way, it would really help your thinking. So in parallel, we consider that each component is connected to the cell directly. Now obviously a resistor can't think, and it's not a good practice to think about the idea of components having thoughts, but in this case, for the case of this resistor, as far as it knows, as much as a resistor can think, it is connected directly to the cell. And same for this one, it is connected directly to the cell. So if the cell has a voltage of say 5 volts, then because this resistor is connected, did I say voltage? I meant PD. If this resistor is connected directly to this power supply, then the reading on V1 is 5 volts because it's connected directly to the cell. And same for R2, it's connected to the ends of the cell, so V2 is also 5 volts. And it doesn't matter how many things I keep adding. I could add a bulb down here, for example, and that would also have a PD of 5 volts because it too is connected directly to the ends of the power supply, and therefore it receives, if you like, the full push on the electrons. Okay, so if we think of it like that, that will help our thinking. Each part is acting as an independent component. It's almost as if the other components don't exist in this situation. So if you're adding things in parallel, it's almost as if it's the only thing in the circuit in terms of its PD. Okay, so last thing is adding cells in parallel. Now, I think OCR is one of the only specifications that deals with this idea, and it's always confusing when it comes up. So you can connect cells in PD, and increasingly this does happen in devices. Now, if I connect the cells like this, let's say they're 1.5 volt cells each. Now, the PDs do not add up in parallel. They'd stay the same. So all I would get from this is I would get, if I connected a voltmeter across the ends, the total PD that I would measure would be 1.5 volts. So you could argue, what's the point in having cells connected in parallel? Well, the reason that cells are connected in parallel is because, let's imagine the current flowing through here is 2 amps. So that's the main circuit current is 2 amps. And that goes off around the rest of the circuit. Because these are in parallel, and because current splits up in parallel, then each of these will provide 1 amp. So 1 amp and 1 amp together, join together to make 2 amps, and we go back around the circuit again. Because each cell is only providing 1 amp, by less current than if it was on its own, what that means effectively is that batteries or the cells will last twice as long. So the reason that you would connect cells in parallel is simply to make them last longer. So remember, going all the way back to series circuits, if you want a bigger PD, then you put them in series. But if you want them to last longer, then you stack them in parallel. So this means you can increase the battery life of a power pack. So for example, the power pack that you might have for a video camera or for something that you needed to last a long time, it may have a series of cells connected in parallel, such that we're not adding the voltages together, or the PDs. All we're doing is we're sharing the load, which means that the current provided will be the same as if we just had one, but because you've got several, then they provide the same amount of current, but giving less each. Not sure I've explained that very well. Let's imagine this is a black box, so we can't see what's inside it. All we know is it's got a PD of 1.5 volts, and it supplies a current of 2 amps. So what's in the black box? Well, it could be a single cell, which provides 1.5 volts and 2 amps, which is fine. However, if I put 2 cells in there instead, then I'm still going to get the same current, but I'm only going to take 1 amp from each cell, which means the cells will last twice as long as if I have one on its own. And if I want to go even further and put 3 cells in parallel, then it would last 3 times as long. So there's no advantage in terms of PDs. The only advantage for connecting cells in parallel is that it will make the battery pack that's within there last longer. So these cells will last twice as long. These cells will last 3 times as long as just a single cell on its own. Okay, thanks a lot.